Today we're going to be talking about right triangle trigonometry. Consider an acute angle theta in the standard position. Create a right triangle as shown with hypotenuse r. The side of length x is called the side adjacent to angle theta. The side of length y is called the side opposite to angle theta. And recall the Pythagorean theorem, a squared plus b squared equals c squared, or more appropriately for trigonometry, x squared plus y squared equals r squared. Solving for r, we have the following. R equals the square root of x squared plus y squared. So here, this is the xy plane, and basically we are extrapolating the right triangle outside of the plane and just drawing a regular right triangle. And a right triangle means that this is a 90-degree angle there. And we have labeled the three sides of our triangle to be called the hypotenuse, the opposite side, and the adjacent side. Now that we have drawn this right triangle, we can define the 6 trigonometric ratios. Sine of theta is equal to the opposite over the hypotenuse, which is equal to y over r. Cosine of theta is equal to adjacent over hypotenuse, which is equal to x over r. Tangent of theta is equal to opposite over adjacent, which is the same as y over x on the xy plane. Then we have these other ones. This is called cosecant, and cosecant of theta is equal to the hypotenuse over the opposite, or r over y. This is called secant, and secant of theta is equal to the hypotenuse over the adjacent, or r over x. And the last one is called cotangent. Cotangent of theta is equal to adjacent over opposite, which is equal to x over y. Now, recall in one of the last units when we were talking about the unit circle, the way that we defined sine of theta was the y coordinate of the terminal point for a given angle on the unit circle. And here, it's y over r. So why is it that those are different? Well, it turns out that they're actually the same, but when we're on the unit circle, remember that when we're on the unit circle, the radius is equal to 1. And so in this case, we would have y divided by 1. And so that's why you have these two different equations here. We have y over r, and in this one we just have y. And again, that is because on the unit circle, the radius is equal to 1. Another thing that I want you to notice when you are studying these 6 trigonometric functions is that these bottom 3 are the reciprocals of the top 3. And what that means is, for example, sine of theta is equal to y divided by r. If you look at its reciprocal trig function, it's equal to r divided by y. And so that pattern holds here as well. One last thing that I want to point out is you might have heard the mnemonic device to help you memorize the ratios for the trig functions, and that mnemonic device is so, ka, toa. And the first letter in each of these represents the actual trig function, so sine, cosine, and tangent. And then the second 2 letters represent which side length of the right triangle we're looking at. So O is opposite, H is hypotenuse, A is adjacent, H is, again, hypotenuse, O is opposite, and then A is for adjacent. So that is the mnemonic device SOHCAHTOA to help you memorize the different trig functions. And then for the bottom trig functions, it's just the reciprocal of those three ones that we just talked about. Note that ratios are equivalent when theta is held constant. We have two triangles here that are similar triangles, and so note that the ratios of their side lengths are the same. Let me draw out two triangles to kind of illustrate what's happening. So let's say I have this angle here being theta, and I draw another triangle, and this is a right angle, and this is also theta. Then the ratio of the side lengths are going to be the same because these are similar triangles and they are proportional. So in both of these triangles, if I call this A, B, C, and I call this D, E, F, if I were to calculate sine of theta in the first triangle, if we follow SOHCAHTOA, sine is equal to the opposite over the hypotenuse. And so if the angle is right here, the opposite is this one here, and then the hypotenuse is C. So this would be B divided by C. And if we calculated sine of theta in the bigger triangle, that would be F over D. But this illustration here is showing us that even though we have different triangles here, because they're similar triangles and angle theta is the same, it turns out that B over C and F over D are actually equal to each other. The symbols we use are abbreviations for sine, cosine, tangent, cosecant, secant, and cotangent. Since any two right triangles with angle theta are similar, these ratios are the same, regardless of the size of the triangle, so they only depend on theta, which again is what I illustrated just a moment ago with the drawings of the two right triangles. It's also important to note the relationship between some of these ratios. For example, cosecant of x is the same thing as 1 over sine of x, and secant of x is the same thing as 1 over cosine of x, and we have these other relationships as well. For example, tangent of x is equal to sine of x over cosine of x. Notice that I'm adding these parentheses in, and sometimes you'll see like your textbook or worksheets not include the parentheses. I highly recommend that you put them just so that you really understand what the input value is. I tend to recommend the same thing for logarithms as well as trigonometric functions. Here below we have this graphic, and in the orange we have the unit circle, and the different trig functions can kind of be seen. So for example, here's our terminal point, and sine is equal to the y value on that terminal point when we're on the unit circle, and cosine is equal to the x value. It also turns out that tangent is the slope of the terminal side of our angle.